Okay, we're going to look at how we can derive the period of a simple pendulum in simple harmonic motion. I'm going to put the textbook page number here in Cutnell and Johnson in our AP Physics text is on page 263 in chapter 10, page 263 at the bottom, and it's got this really small picture, and 10.4 is the section, not even a full page, that talks about how we can find, as we did for the mass spring system, we found angular frequency omega, alright, which we know is equal to 2 pi f, and we're also looking for the period t. Now for the mass spring system, we found that angular frequency was the square root of k over m, and we found for the mass spring system that the period was 2 pi square root m over k. Alright, so these are things we found out already with the mass spring system. We used our kinematics for rotational motion, our knowledge already of second law, Hooke's law, and how we can find position, velocity, acceleration of a harmonic oscillating particle. Alright, so this stuff up here, this was from our mass spring information. Okay, we'll read from the book and then give a little elucidate some of why they choose, or what they're doing with the variables that they choose to use. This is in 10.4. The simple pendulum consists of a particle of mass m. That's my orange dot over here. All right, you can see it at 3 different places. This is my image of a pendulum at 3 different points. It has a mass m attached to a frictionless pivot p. There's frictionless pivot point p by a cable of length L. So this dotted line is length L. Okay, it's not going to expand or contract, it's rigid, and that length L, that cable string, is of negligible mass. When the particle is pulled away from its equilibrium position by an angle theta and released, so by angle theta we mean here is angle theta, okay, just like we did in class, it swings back and forth, as figure shows in the book, and my figure does too. By attaching a pen to the bottom of the swinging particle and moving a strip of paper beneath it at a steady rate, we can record the position of the particle as time passes, and we see, as we have seen in the same way that our LabQuest recorded it, we get some variation or phase-shifted function that is the sinusoidal. Okay, so we know this much so far. Gravity causes the back and forth motion about the axis p. The rotation speeds up as the particle approaches the lowest point and slows down on the upward part of the swing. Eventually the angular speed is reduced to 0 and the particle swings back. A net torque is required to change this angular speed. The gravitational force mg is what's producing this torque. Let's draw mg as a vector in pink. Why not? Here is my particle at its maximum displacement. That's not a straight line. Let's use actually a line that is straight, and I'll put an arrow on it, and that'll make me feel better. Here we go. It's much better. Okay, straight down towards the center of the Earth, and this has the value mg. There it is. We know that force is acting on the pendulum. Let's continue. The tension T in the cable creates no torque because it points directly at the pivot P, and therefore has a 0 lever arm. Alright, so that has to do with the angle between the lever, or the axis of rotation, and the force of tension. We will call the force of tension, simply to illustrate it. Let me get my straight line with an arrow again. Where are you? Let's make a little dotted one. Green. Here is the tension. Okay, except that we need it to actually be on top of this other line. Can we do that? Let's just delete it and draw it in pen. Alright, so we have some tension that's right along here towards the center, and we can just call that F sub t to make clear that it's not just t, which we're also using for the period. Okay, so the magnitude of this torque is the product of the magnitude mg of the gravitational force and the lever arm L, little l, so that torque equals negative mg little l. Now, where did they get this little L from is the question, and that's what we're going to look at. First, before we say what it is and why it's introduced, let's look at our component of the gravitational force that's actually contributing to the torque at this very point, at this instant. As you can imagine, when the pendulum comes down here, when it gets to its equilibrium point, where we said there's zero net force and zero acceleration and maximum velocity, when it gets to that point, I have no horizontal or x-axis component of gravity anymore. Of course, I still have this same value that I drew over there. This is still mg. And tension has actually increased to balance it out. Alright, so F sub t has increased. But there's clearly, at this point, no x or horizontal component of mg. However, everywhere else there is. In red, we'll show it. This is now what we can call, we'll call this the tangent to the circle. Okay? And I also have a component we'll do in blue. Alright, if we break down our mg, there's the other component. It's pretty good. And my blue component here should balance out my green ft, the tension. Okay? And my red component of mg is the component of that force that is contributing to the net torque. We'll see what those values are. Right? Excuse me. We know, because my center equilibrium line is parallel to pink mg over here, that therefore this angle is also equal to angle theta. Given that that is equal to angle theta, we know that the value of our x component in red of the force of gravity, so I'll put fg x component is equal to mg sine theta. And we know that the blue component there, which we'll say fg y component, is equal to mg cosine theta. It's adjacent to that angle theta. Now, I didn't do a very good job talking about positive or negative directions. This torque that's going to be produced, and it's being produced at this point where I've drawn these vectors, at that point it's equal to mg sine theta. Okay, and it's producing a torque that we have to say is negative. If it has a positive angular displacement, the torque is pulling it back towards the equilibrium line. So really we would say here at this point, I'll do it in red, the torque external here, is entirely produced by that red component of gravitational force. And so that external torque is mg sine theta, times the radial distance to the axis of rotation, which we said was capital L. Alright, so that's one way to look at that particular point. What is the external torque? Now in the book we're saying on page 263 that the torque is the product of the magnitude mg of the gravitational force and the lever arm little l. So, why and what is that? Here's where they draw a little l. We're going to erase my stuff I have right here because we're not talking about this position. But they introduce this little l because we have a constantly changing everything. The position, the velocity, the acceleration, and the force are constantly changing. Okay, but we are getting simple harmonic motion, and we've said before in class only at small values of theta. So this little l is introduced because we need to be able to talk about where, that's an eraser, where they have drawn in their image in the book, this little l is, this length, which is perpendicular right there to the equilibrium position. And we also have a name that I will draw in darker red for this section of arc, which they'd call S for the arc length. You can see for large values of theta, and this is a large value of theta, it's exaggerated so you can write inside the angle, that little l in blue is nowhere near the same length as S, the arc length. But for very small values, let's say I make a really small value, really small arc length right there, and I draw little l again, they're almost right on top of each other. As the angles get smaller and smaller, they approach the same length. And when this line right here is equal to the orange line, the component of gravitational force right here is almost entirely the same throughout this entire part of the swing. So we need to find a way to talk about small angles for this pendulum, because that's the only time the torque is going to remain approximately the same. So we'll get rid of these right here, and we'll show how we're going to do that. The book does it, not really telling us in too much detail how, by introducing s and little l. Alright, so first we're going to see how these introduced values of s and l, particularly little l, are related to what the book is saying when they say the torque is equal to the magnitude of mg times little l. So if I have what I arrived at here, just breaking down, resolving my gravitational component that's producing the torque on the pendulum, and I have to say, I was just saying before we introduced s and l, that this needs to be a negative value because it's a restorative torque. It's bringing the pendulum's bob back towards the equilibrium position. So if this theta, orange theta, is a positive angular displacement, then we can see that the torque is in the opposite direction. It's bringing it back towards its equilibrium position. Now, how do we get to the torque being equal to negative mg little l? Well, we can see from our diagram geometrically, and we'll do it in our lighter blue here, that little l must be equal to the hypotenuse, big L, times the sine of theta by construction. And therefore that big L is equal to little l divided by the sine of theta. Okay, so they're saying take that, alright, and substitute it back in for big L. So if we do that, we get torque external. Let's go back to red. If we do that, then we get next torque external. Because it is a restorative force producing a motion back towards the equilibrium position, we say it's minus mg sine theta times L, what we just solved for, which is little l divided by sine theta. And then you can see we clean up that with one step, and we get torque external equals minus mg little l, and that's what we have halfway through the paragraph in the book. Torque is minus mg little l. So let's put a little box around that for now. That's how we can get there from the, at least to me, resolving the components of force up top there of gravity, and we take their geometric definitions of where L and S are. That's little l and little s. Let's see what they say. The minus sign is included since the torque is restorative. It acts to reduce the angle theta. The angle theta is positive while the torque is negative. And the lever arm, the little l, is perpendicular distance between the line of action mg and the pivot p. In figure 1020, which is their small image at the bottom of the page, L is very nearly equal to the arc length S of the circular path when the angle theta is small, about 10 degrees or less. Furthermore, if theta is expressed in radians, the arc length and the radius L of the circular path are related according to S equals large L theta. So we had mentioned already that if we have a very small angle theta, little l and S arc length approach one another. We also had our go-between equations for rotational kinematics, which we'll use here. We said arc length was equal to theta times the radius r, just like we had our linear v. Tangential was equal to omega r, and tangential acceleration, linear acceleration, is equal to alpha r. Well, we're going to use this one. Okay, and we're going to say that s is equal to theta times the radius, and that radial length is big L. Okay, well, we said that also at small angles, s approaches little l, which means we would have little l equals theta times big L. And then we can go back down here and look what our, in purple box, torque external is minus mg little l. Well, we take this guy, we plug it in down here for little l, and now we have a value that we can work with next. We will rewrite now in torque external has become, given a small value approximately equal to minus mg, the restorative force, times what we're substituting in for little l, this value up here just above where we're writing now, theta times big L. Alright, so that's how they get what they have there in the, just below that second paragraph. Torque is approximately equal to. Let's see what else they say. Furthermore, if theta is expressed in radians, the arc length and the radius L, big L of the circular path are related. According to S equals L large L theta, it follows then that L is approximately equal to S, which equals L theta, and the gravitational torque is. Okay, so that's what we just did. So that's what we got. Let's put one more box, since this is where we are now. The term MGL has a constant value K prime, independent of theta, for small angles. MGL has a constant value for small angles. So here's where we have an approximation and why we have to say we have small angles for a pendulum that's going to exhibit simple harmonic behavior. Now also remember we have up here, which is what we're about to use, our values that we found for the mass spring system from Hooke's law. We're about to do a very similar thing. We're going to say that this expression that we have, let's relate it to, we've gotten down to a net external torque. All right, that's the restorative torque, bringing it back to equilibrium. So let's remind ourselves that we have a restorative, I'm going to call it restorative force because it's not a spring force. We have a restorative force that is equal to minus kx. Okay, but for us with this pendulum where we have a rotational situation, we have a torque restorative that is equal to some constant times, not x, but theta. And we just found out what our torque restorative was. It was minus mg theta big L. This is what we want because we have the big L, which is the measurable length of our pendulum, and theta, the relatively small angle, and the weight of our bob at the end. And this equals minus k theta. Now what? Well, this value for the torque that we found, minus mgl theta, we can use to relate, as we've done with the Hooke's law, to figure out how we can use k. So let's simplify this from what we have. We have minus signs that are going away, a theta that is going away, and so we have mgl left over. Mg, and remember this is big L, the length of the pendulum equals k. Let's box that one. Now we have an analog for the spring constant, except this is for the based on the torque produced. This is based on the torque produced by the gravitational force acting on the pendulum. So we have this value for k. So we can go back and we can look at these values we have that we're looking for. We're looking for omega and t, angular frequency and period t. So let's substitute in our analog that we found. Let's find out what that analog is both for omega and for t. So here's, we'll start with omega. Omega, which is equal to the angular frequency 2 pi f. For the mass spring system, we said that was the square root of k over m. Now for us, we have a rotational situation where we have to deal with a moment of inertia, not just a mass. Remember, a moment of inertia is mr squared. We don't have any strange geometry or distribution of mass, so there's no coefficient in front of it. And so our moment of inertia for our pendulum is ml squared, because the radius is big L, the length of the pendulum. So that gives us for our omega, we have the square root of k. Well, we just found our k was mg big L, divided by, not the mass, but the moment of inertia, ml squared. Notice we can simplify this. M's go away, L up top, and one of the L's down below go away. We have the angular frequency omega for the pendulum as the square root of g divided by big L. Okay, so there is our angular frequency for the pendulum. Now we do a similar substitution for our period. Let's remind ourselves, what did we get for the period? For the period of the mass spring system, period, yeah, purple's fine. The period of the mass spring system we said was equal to 2 pi times the square root of m over k. Whoops, that's not an m. M over k. Again, we need to substitute in our moment of inertia for the m and our value, our k. I'm talking about this k over here that we've found for the pendulum to get what the period of the pendulum should be. Let's substitute these values in. We get t equals 2 pi times the square root of moment of inertia ml squared, because the radius is equal to big L, divided by k, which we found was mg big L, mg big L and ml squared. Okay, looks good. We simplify. M's go away. One of my L's goes away. And so we have for the period of the pendulum, capital T period equals 2 pi square root big L, the length of the pendulum, divided by g. Period of a pendulum. Period of a pendulum down there. And angular frequency of a pendulum right there. And there's our picture. And remember, these were the values we found for the mass spring system in the other video. 263 is the page to see the small amount that they have written there. This is how I understood it. Anything, let's just see what the last paragraph says. Well, I guess the final note is, the final note is the mass of the particle has been eliminated algebraically from this expression. That's important to see. So only the length L and the magnitude of little g, the acceleration due to gravity, determine the frequency of a simple pendulum, or the period. If the angle of oscillation is large, the pendulum does not exhibit simple harmonic motion, and this equation for angular frequency does not apply. Might also be worth mentioning, this provides the basis for using a pendulum to keep time, for the example, in grandfather clocks.